access scheme, which in short also abbreviated as NOMA, non-orthogonal multiple access. So you might be aware of various orthogonal multiple access schemes as TDMA, time division multiple access. Second is CDMA, code division multiple access. And the third one is orthogonal frequency division multiple access, or frequency division multiple access, and each subcarrier is orthogonal to each other. So this is called, these three are the basic orthogonal multiple access schemes. It means if our base station is serving two users simultaneously, so either they will be differentiated or the data will be transmitted to user 1. If particularly we talk about TDMA, so if this is the total time interval which is allocated to the base station in order to transmit information U1 and U2, what it will do, it will transmit information for some fraction of time to U1, and for the other fraction of time or other time for the t minus tau time, if t is the total time. So for tau time it will transmit data to U1, and t minus tau it will transmit data to U2. So this is called TDMA, means both users are differentiated or the data is transmitted to user U1 and user 2 in different time slots. What happens in code division multiple access? In code division multiple access, two different codes are assigned to user 1 and user 2. So these two users are different in codes, or you can think it as a key. So two different keys are allocated to U1, U2, and they are different. Their difference is in code. In frequency division multiple access, the two users are served in different frequency slots. So this is the three orthogonal schemes, or in short we say in TDMA the user 1 and user 2 are served in two orthogonal time slots. In CDMA, two orthogonal codes, and in OFDMA, two orthogonal frequency slots or frequencies. But what happens in non-orthogonal multiple access? Both the users U1 and U2 are served over same time and same frequency slot, but we differentiate it in power. What do we mean? What do I mean when I say that two users are different in power? It means base station will transmit P1 power to P2 and U1 and P2 power to U2. If total PT power is allocated to base station, then user 1 will be served with some other power, some power P1, and U2 will be served with the other power, with some amount of power P2, and the total power should be the total power allocated to base station. So what happens? P1 does not equal to P2 in generally, and we allocate more power to the user. The higher power is allocated to the user with higher channel gain, So let's try to understand it. This is our base station. This is user 1, this is user 2. And H1 is the channel coefficient between base station and U1, and S2 is the channel coefficient between base station and U2. This H1, S2 can be Rayleigh or Rician according to the environment. So what would be the gain for this link, base station and U1? This will be the gain, and for the user 2 and base station link, the gain will be this. So let's So if P1 is the power allocated to U1, we can say that P1 is A1 times PT, and the P2 is A2 times PT. And since we know that P1 plus P2 should be equal to P2, therefore A1 plus A2 must be equal to 1. So A1 and A2 are also known as power allocation coefficients. They decide the amount of power which goes to the user 1, and A2 decides the amount of power which goes to user 2. That is why it is called power allocation coefficients. So now just write what is the signal or received signal at user 1. So Y1 is, if X1 is the symbol which we want to transmit to U1 and X2 is the symbol which we want to transmit to U2. So here we have a modulator, and X1 modulator is producing X1 and X2. X1 and X2 can be either BPSK, QPSK, any signal. So just we write that X1 is the signal intended to U1 and X2 is the signal intended to U2. So since we are using A1 PT power in order to transmit X1, so, and H1 is the channel between this, so H1 times root of A1 PT X1. Why we are doing it root? Because the power of this whole should be A1 PT, and we are assuming that here that X1 and X2 we are producing, they have unit power, and all the power is actually lumped in this parameter A1 PT. So H1 root A1 PT X1 plus H1 root A2 PT X2 plus, and this whole signal will be received by U1. Or if I say more elaborately, the base station first superpose the signal which we want to transmit to U1 and U2. So X1 is the signal which we want to transmit to X1 multiplied with the power allocated, square root of power allocated, plus root of A2 PT X2. So this is the superposed signal which this base station will transmit, and this whole signal will go through this channel H1 times, we call it XS, X superposed signal. So H1 times XS plus N1. So Y1 will receive this, and Y2 will receive H2 superposed signal plus N2. That is what I have written here. So H1 root of A1 PT X1 plus H1 root A2 PT X2 plus H2 root A1 PT X1 plus H2 root A2 PT X2 plus N2. So this is the two signals, Y1 and Y2. But there is a information, or there is a concept of SIC, which is called successive interference cancellation. So in NOMA, this SIC is a very important concept, that is called successive interference cancellation. Successive interference cancellation. So what we have seen here, that Y1 receives the signal, the symbol intended for himself as well as for the other user. Similarly, user 2 also receives the signal corresponding to U1 and U2 both. But what would happen, since user 1, you can say that if gain of user 1 is higher, in general, if U1 is closer to base station, the channel gain will be higher, because channel gain is inversely proportional to 1 upon d to the power some path loss exponent. So we call Y1 as near user or U1 as near user and U2 as a far user. Since channel gain of U2 is less and channel gain of U1 is more, therefore U1 is nearer to the base station and U2 is the far from the base station. What would happen? The far user will first the near user will first decode the x2. x2 is the symbol which is intended for user 2. So in order to do so, what we do, we provide more power to the far user as compared to the near user. So if the U1 is near user and U2 is the far user, what will we do? We will transmit more power, we will allocate more power to the far user, and therefore the near user, since we are allocating more power to the far user, here if you focus on this equation, if A2P2 is higher, the near user, in near user this part will have higher contribution. So what will near user do? It will first decode this signal of user 2 and then it will cancel. It will first decode what is the value of x2 and then it will cancel the signal. So therefore it will only left with the signal this. So the near user will first decode the signal of far user, and which is allocated, far user is allocated more power. This is rule of the thumb in NOMA, that far user is allocated more power or higher power. So the total signal is y1 h1 root a1 pt x1 plus h1 root a2 pt x2 plus n1. So user 1 will first decode the signal x2 from y1, and then what will it do? It will subtract this part. So after SIC means decode the signal of user 2 and then subtract it from the received signal. So y1 will be subtracted with this amount. So if most of the time we assume that this decoding is perfect, it means x2 hat is equal to x2. So this will completely go away. And if SIC process is not perfect, then there will be some error left. But for now we are assuming perfect SIC, means x2 hat is equal to x2. So y1 will be h1 root a1 pt x1 plus n. So what is the rate at user 1? Log 2 1 plus, if noise is 0 sigma square, if you remember by the Shannon's formula, ex1 square is, we have assumed that it is 1 divided by sigma square. So user 1, the data rate achieved for the user 1 is under the perfect SIC, Similarly, what would happen to user 2? User 2 is receiving this signal h2 excess, which is the superposed signal, and this noise is added. So H2 root A2 P2 X2 plus H2 root A1 PT X1 plus N2. Okay. So user 2 will consider, since the power allocated to user 2 is more as compared to user 1, therefore this component will not be highlighting at the user 2. So what will user do? User 2 will consider this whole thing as a noise and it will decode only X2. So user 2 decodes X2 by considering user 1 signal as interference or as noise. Because user 2 does not have any choice that it can first decode the signal of X1 and then it can subtract, because the power allocated to you is not that much that it can highlight or it can come out as compared to X2. So therefore the rate of user 2 will be log 2 1 plus. This is a signal power. Signal power is mod of H2 square A2 PT, and of course EX2 square is 1, so we are not writing it here. Noise is sigma 2 square mod of H2 square A1 PT. So this is the rate of user 1. So we can write that in NOMA scheme log 2 1 plus mod of H1 square A1 PT divided by sigma square, whereas the user 2, the achievable rate of the user 2 is this noise at the user 1 and user 2 can be different, but in our case we are assuming that they are identical. So as you can see that rate of user 1 and user 2 depend upon the power allocation coefficient A1 and A2. And therefore, if we take different values of power allocation coefficients, these values of R1 and R2 will be different, right? Power allocation decides the value of R1 and R2, right? So there are various power allocation schemes depending upon the metric. For example, we want to optimize R1 plus R2, then we have to use some other strategy in order to allocate our power allocation. That strategy can be strategy 1, right? The other one can ask that R1 can be more as compared to R2, then we have to accordingly decide the strategy or the power allocation strategy. Now one can also question that how can you show that NOMA is better than OMA or orthogonal multiple scheme. So let's just write what is the rate we receive for the OMA scheme with TDMA. Let's say just we are doing TDMA. So in TDMA I told you that if there are two users, for some time user 1 will be given the whole power. If PT is the total power, the whole power will be given to user 1 for some time duration, and for the rest of the time duration user 2 will be given the whole power. So let us assume that we are dividing our power or time by half, means for half the time, therefore I am writing this half to 1 plus mod of H1 square. The complete power will be transmitted to user 1. And for half time, this complete power is given to user 2. But because of this factor half, you can check, for example, you want R1 plus R2. Your metric is R1 plus R2, so you just plot the R1 plus R2 by considering H1 square as 2, H2 square as 1, and PT by sigma square as 10. And x-axis you can take A1. A1 will be from 0 to 1, and therefore A2 will be 1 minus A1 because I have already told you that A1 plus A2 is equal to 1. So just put various values of A1 and A2 as 1 minus A1 here, put A2 is equal to 1 minus A1 here, and just run this for various values. You will see R1 plus R2 curve, right? Maybe this type. And then you compare, just do it for TDMA and check. So for OMA case, with the given parameters, your R1 will be 0.5 log 2 1 plus 20, because PT by sigma square is 10 dB. 10 dB is in a linear scale is also 10, right? So 10. R2 is 0.5 log 2 1 plus H2 square is 1, so it is 10. So it is 0.5 log 2 21. It is 0.5 log 2 11. In NOMA case, what would happen? R1 is log 2 1 plus 2 into 10, and R2 is into A1. We are forgetting the factor of A1, so log 2 1 plus 20 A1 log 2 1 plus PT by sigma square. You can write it first, mod of S2 square A2 PT plus mod of S2 square A1 PT plus sigma square, which is equal to log 2 1 plus 10 A2 divided by H2 square is 1, A PT by sigma square is 10 A1 plus 1. So just check it. So now put values of A1 and A2 and just calculate it. So you will see, just R1 plus R2, do R1 plus R2 and run it for both OMA